Hello everyone, my name is Gaurav Mahajan and thanks for joining this session. There's been a number of important empirical work in reinforcement learning recently, and this has led to a lot of excitement to critically understand these algorithms. One such class of successful algorithms in R is policy grading methods, and the work I'm presenting today is an attempt to theoretically understand these methods. This is joint work with Alekh, Sham, and Jason. So why do people love policy grading methods, and why are they so widely used in practice? Well, they're very simple to implement, since you can estimate the gradient using only a simulator. These methods work great in environments with large state and action spaces, and are basically optimizing the cost function of interest for essentially monitoring. But in the end, what we actually want are good policies. So the question is, does policy grading methods converge to good policies? And even though they're used so extensively, we know very little about the theoretical properties of these algorithms. In fact, we only know that these methods converge to a stationary point under sufficient smoothness conditions. In this talk, I'll provide a beautiful characterization of policy grading methods to understand what's good about these algorithms and what are their shortcomings. Actually, very little is known about these algorithms, even in small state spaces. So we'll start with small state spaces and discuss the optimization landscape there. And then we'll move on to large state spaces and look at the question of functional approximation. But before we describe these methods formally, let's start by reviewing the basic RL framework. There is an underlying Markov decision process with state space S, action space A, dynamics of going from one state to another state given an action, reward of taking action A in state S, starting state distribution rho, and discount factor down. At each step, an agent is in some state, choosing an action to receive some reward and transitions to a new state. The objective of the agent is to learn a policy pi, which is a function from a set of states to distribution over actions, which maximizes the expected discounted sum of reward. Okay, so what's policy grading algorithm? It's a very simple grading-based algorithm. You have some objective that you want to maximize. In this case, that's the value of the policy. So you change the parameters of your policy in the direction of the gradient. Slight caveat here is that instead of using distribution rho, you might want to consider a slightly different or very different distribution mu for better exploration. We'll see later what role this distribution plays in various policy grading methods. These methods optimize over a parameterized policy class. So let's consider some very natural policy classes where probability of taking action A in CX is proportional to exponential of some function. For small state spaces, we'll consider Softmax policy class, where we can afford to have a single parameter for each state in action. This policy class is complete in the sense that you can represent any policy in this class. For large state spaces, we'll consider somewhat restricted class, that is the log linear policy class, where we have some features in linear dimensions and the function is linear in those features. The last class we'll discuss is neural policy class, where function is represented by the neural network. Now I'll discuss policy grading methods in small state spaces. Throughout this part, we'll assume access to exact gradient and later show how to deal with sample-based gradients in the large state space setting. The underlying question in this part is, do policy grading methods converge to the optimal policy? Our first result is that standard convex optimization results will not help us in our endeavor, since there exists a simple MDP, which is the image on the right, such that our objective function is non-concave for the softmax policy class. So let's dig deeper into this issue and write the gradient expression for softmax parameterization. But before we do that, we'll first define some new notions. The first one is state visitation distribution, which is essentially discounted probability of visiting a state S, starting from some state distribution mu and then following policy. Another notion we need is Q-value function and advantage function. Both are pretty standard in R. Q function is the expected to-go reward when you start with state S, take action A, and then follow policy pi. Advantage function is just the advantage of taking action A in state S versus just following policy pi. With this, we observe that the gradient of the value function with respect to the parameter for state S in action A has a term for discounted probability of visiting state S, advantage of taking action A in state S, But there is also a term for probability of taking action A in state S. And this is troublesome because any policy that is nearly deterministic will have gradients close to zero. So let's summarize the optimization landscape. The objective function is non-concave. The standard techniques in non-concave optimization, gradient domination arguments, will not help us here because these arguments are usually of the form small gradient implies closeness to optimality. But as you observed before, there exist suboptimal policies with arbitrary small gradient. But in spite of this difficulty, we'll show a positive result. The policy gradient algorithm asymptotically converges to the optimal policy. To prove this statement, we have to argue about the dynamics of the policy gradient. In fact, we show that the limit of the value function exists, and policy gradient ensures that this limiting value cannot be different than the optimal leader. But is there a way we can get some kind of convergence rate which is polynomial in number of states? What we observed in the vanilla policy gradient method is that small action probabilities lead to small gradients, which eventually lead to slow convergence. A common remedy used in practice to ensure that the action probabilities do not become too small is to use some kind of entropy regulation. In our case, we'll update the loss function to include the penalty of the KL divergence between the policy part and the uniform policy. We proved that when the exploratory distribution mu is uniform, policy gradient with relative entropy regularization not only just converges to the optimal policy, but also converges at a rate of 1 over t with polynomial dependence on number of states in number of actions. A surprising side effect of adding this entropy regularization is that unlike policy gradient, small gradient here actually does imply closeness to the optimal solution. But the gradient is still dependent on the state visitation distribution, leading to polynomial dependence on number of states and number of actions. So is there a way we can get a better convergence? For that, we'll consider another natural algorithm, which is natural policy gradient algorithm introduced by Kakade in 2001. This algorithm uses Fisher information-based preconditioner to transform the distance matrix to move more near the boundaries of the probability. For the Softmax parameterization, there is a much simpler form for this algorithm, where the updates in the parameter space do not depend on the state decision distribution, and the updates in the policy space are very much like multiplicative update when a non-concave maximization set. We show a very surprising result from natural policy gradient algorithm, showing that it converges at a rate of 1 over t, without any dependence on number of states, action, or any kind of condition. The proof for this algorithm is super clean and mostly follows a mirror descent style analysis. Similar analysis was done by Evan et al. In a slightly different setup and with slightly different rate. Now I'll talk about policy gradient methods in large state spaces with sample-based gradient. The question we'll consider here is how well do policy gradient methods deal with function approximation? The first restricted policy class we'll consider is log linear policy class, where probability of taking action A in state S is proportional to exponential of some linear function. Natural policy gradient update for this policy class is equivalent to finding the best linear fit in the policy space features, and is essentially solving a regression problem. This update is similar to the update in the natural active predicate. For now, let's make this strong assumption of realizability where the Q function is linear in the features. Also, we'll run a regression to absolute error, which is very cheap because we can actually do this using only samples from distribution mu. So this is basically just doing least square regression. There's another quantity which is going to govern our convergence rate, which is relative condition number. This quantity captures the expression provided by the distribution mu in the feature space with respect to the optimal state action measure. This turns out to be equal to density ratio for the Softmax parameterization and is generally upper bounded by the concentrability condition. Under these conditions, we show that natural policy gradient algorithm converges to the optimal policy at the rate of 1 over root t with logarithmic dependence on number of actions. Plus, there is a mild error due to supervised learning, which can be made pretty small, since this is just going to be the regression error, which goes down as d divided by number of cells. This algorithm generalizes pretty nicely to a neural policy class, and we have a forthcoming addition to our paper discussing this case. Similar analysis was done by Liu et al. Recently in the NTQ regime for the neural policy class. In summary, our paper provides a comprehensive set of techniques for policy-gain methods with regards to both optimization and function approximation. We show global convergence results for policy-gain methods, whereas earlier only convergence to stationary points per node. We then show how policy-gain methods deal with function approximation and sample-based gradients. We have a forthcoming addition to our paper with improved theory for non-realizable. Please check out the paper for proofs and other results that I skipped over in the slides, notably the lower bound construction to emphasize the role of exploratory distribution and results on deck parameterization, which are also considered by Bandari et al. There are a lot of exciting new questions in the area, primarily how to design better exploratory distributions new in practice, and if the rates discussed in the paper are optimal, or is there a corresponding error. Thank you for listening.